Alright, so what I'm going to do here is kind of a whirlwind through the basics of electrochemistry, kind of getting down all the terminology. So the first thing you have to understand is that electrical current is the flow of electric charge. So we talked about balancing redox reactions, and what's happening is the thing that's being oxidized is giving off electrons. The thing that is being reduced is taking in electrons. Well, when you pass these electrons, that is now flow of electrons. So it's flow of electrical charge. Therefore, we have some electricity. And so that's what electrochemistry is all about. We're talking about the flow of electrons to get an electric potential going on there. So an electrochemical cell is the generation of electricity through redox reactions. Okay, we do this in an electrochemical cell. I'll show you a picture in a minute. And there are two types. There's the voltaic cell, that's also called a galvanic cell. And this is a cell that produces electrical current using a chemical reaction that's spontaneous. In other words, it's thermodynamically favorable. An electrolytic cell is a second type that consumes electrical current. So, in other words, this type of cell is not thermodynamically favorable, so we're taking an outside source of power, a battery of some sort, and making the non-spontaneous or the thermodynamically unfavorable reaction happen. It's going to consume electrical current. So a half cell acts as an electrode, and a half cell is going to be where the half reaction takes place. So we've already balanced the half reactions when we did our balancing of redox reactions. Now the half cell is just where that half reaction takes place. So this is what a typical voltaic cell looks like. You're going to have the anode and the cathode. Electrons always flow from the anode to the cathode. The anode is where oxidation takes place, cathode is where reduction takes place. Then you have to have this salt bridge in the middle to replenish ions. If you did not have the salt bridge, you'd get a buildup of negative charge at the cathode and a buildup of positive charge at the anode, and it would stop the flow of electricity. So that's what that's for. Obviously, in this case, zinc is going from the solid form to the dissolved form of zinc 2+, and copper is going from the dissolved form of copper to the solid form of copper. And in the process, we're using that passing of electrons as an electricity source. So the half cells are connected by a wire, and the electrons spontaneously flow from zinc to copper. The reason this happens is due to a potential difference. A potential difference is very similar to a stream of water. So when you have a stream of water, gravity is the force. It's making the water flow from a higher altitude to a lower altitude. In this case, we're going from a high potential to a low potential, and the electrons will flow that direction. The measurement of flow is amperes or amps. 1 amp is 1 coulomb per second. A coulomb is a unit of charge, and so that's telling you how much charge is passing per second. An electron has a charge of 1.602 times 10 to the negative 19th coulomb. So you can calculate, if something has 1 amp, you can calculate how many electrons are flowing per second if you wanted to. You don't usually want to, but you could. So the potential difference is a measure of the difference in potential energy, usually in joules, per unit of charge, usually coulombs. So we're looking at how the potential energy changes per unit of charge over the course of the reaction. So if we, the SI unit of potential difference is the volt, and a volt is a joule per coulomb. So what this means is that a potential difference of 1 volt means a charge of 1 coulomb experiences an energy difference of 1 joule between the two electrodes. So 1 coulomb will change 1 joule between the two electrodes. This difference has a couple of names. I usually call it the cell potential, but the potential difference is also what I've said so far. It could also be called the electromotive force or the EMF. You can use them all interchangeably, it doesn't really matter. So what the point of all this is to combine two things, one more likely to undergo oxidation and one more likely to undergo reduction. And in that case, you can get a large difference in a positive cell potential, which allows spontaneous flow of electrons. The cell potential depends on concentrations and reactants, so we went ahead and made a standard, and that standard is 1 molar concentrations for all products and reactants and 1 atmosphere pressure for gaseous reactants. So just keep that in mind. The standard is that little degree sign. So if it doesn't have the degree sign when it says E cell, that means it's not at standard conditions, and we'll talk about that later. As I already mentioned, the anode is where oxidation happens, so the electrons are being given up. The cathode is where those electrons are taken in, so where reduction happens. Electrons always flow from anode to cathode, and I already talked about the salt bridge, so hopefully we are good there. Alright, so cell notation. This is another way to write it without having to draw the whole picture. We put the oxidation half reaction on the left and the redox half reaction, the reduction half reaction on the right. Substances in different phases are separated by one vertical line. The double vertical line represents the salt bridge. If you have things in the same phase, like in this example here, you have the permanganate and the H plus and the manganese 2 plus all in the aqueous phase, so you just separate those by a column, and then the electrodes are usually what you're going to see on the far left and the far right. So just keep that in mind. We do have to have a standard here, so we're looking at potential difference, but we're always looking at the difference. So to get standards for one to use for one half reaction and another, we compare everything to hydrogen. The same is true with altitude. If you think about it, we always talk about altitude differences, and we compare that to sea level. Well, why sea level? Because we chose it. And that's kind of how this works too. We decided that the hydrogen electrode is going to be 0, and we compare everything else to that, and that's how we get standard electrode potentials. Now, to calculate the cell potential of an electrochemical cell, you just take the cathode reduction potential and you subtract the anode reduction potential. So you'll have this chart that I passed out. It has all reduction potentials on it, and you just do cathode minus anode as written, and typically the oxidation part's going to have a negative number. Not always, though. It actually just needs to be more negative. And then the reduction part needs to be more positive. Whether that means they're both negative or both positive, it doesn't really matter. But to get a positive cell potential, the cathode has to have a more positive reduction potential than the anode. Alright, I think that's where I'm going to stop for this one.